and I'm going to start sharing my screen. Again, this chapter we've been looking at that transformational geometry. The activities and the homework are due on Friday. This will be the end of the class. Today, I think this will be the last day for chapter 11, unless people have additional questions. On Wednesday, we'll start with that again. So please, by Wednesday, I'm going to ask that you have a compass and straight edge. As we go through the notes on constructions with compass and straight edges, we'll be flipping back and forth between me showing you actually doing a construction and filling in the questions in the notes packet. I'm thinking that this time around, the notes packet will probably be much more filled in by hand than digitally. So I will try to upload pictures of the chapter 12 notes at the end of the day, in addition to the notes packet that we're writing on. But I digress. Friday, we finished filling in the notes packet for chapter 11. Did anybody have questions on anything that we've done note-wise with chapter 11? If not, with the chapter 11 homework, again, I'm going to reiterate that a lot of it is drawing diagrams. You need to draw your diagrams on dot paper if asked, or graph paper if asked. Again, I believe that there are dot paper that you can print out in Blackboard. There's graph paper you can print out in Blackboard if you don't have graph paper of your own. There's also, you can just Google up dot paper, and you can just Google up graph paper and get pictures of them. Does anybody have questions on any of those homework questions from chapter 11? Does anybody want to look at any of those textbook problems? Wow, you guys are quiet. Does this mean that right now everybody's totally on top of their game with the homework and don't have problems with any of them?
On page 588,
Yeah.
for number 2 and 5, do we have to like draw them out and divide them, or like?
Let's look at those questions, because I have to apologize. I did make the answer key a while ago and I don't remember exactly what they were. So 588, number, oops, they've got to be on that next page, 2. Yes, you would need to draw those pictures and draw in the lines of symmetry. And 5, yes, you'd need to draw those pictures and draw the reflections.
Okay.
You can draw them on regular paper. You can, if you want it very precise, you can probably trace them. Otherwise, you can freehand them, sort of. Again, it would be a much better show of your work if you like used a straight edge for them to make your lines straight. Any other questions?
Can we go over 10 and 15 on page 576?
Sure.
All right, thank you.
You said 10 and 15?
Yeah, thank you.
10 says we've got this equilateral triangle. It has a center at O, and it's pointing upward from its horizontal base. We want to describe all of the non-equivalent, which means different, rigid motions that move the triangle to point downward. So we want to picture doing a transformation that takes that triangle, and instead of pointing up, it points down. But we want to leave that center fixed. We don't want that center to move. And so I guess one thing that we could do is we could just rotate the paper upside down, right? If I turn it upside down, it would be 180 degrees and the center would be O, right? If I turned it completely upside down. But see, is there anything else that we could do? Let's change colors a little bit. Could I picture putting a line parallel to this base, and if I folded it over that line, folding it over that line, wouldn't it turn it upside down? And that point would be the same. Huh, are there any other lines that I could fold that over and have it turn upside down? Any ideas? Vertical line wouldn't do it. Vertical line, it would have symmetry. Can anybody see any other lines that we might be able to fold it over? Well, you guys are quiet. What if I took a line? Yeah. What if I took a line parallel to one of the other sides? Do you see this green line that I'm drawing in? This point would go here. This point, if I folded over the green line, would go here. This point, if I folded over the green line, would go here. And wouldn't that turn it upside down? And so I could reflect it over a line parallel to that side. Do you think it would work if I reflected it over a line parallel to the other side? I think so. I think there's a couple of line reflections. And over here, if we flipped it all the way up around, 180 degree rotation would do it. Is there a smaller rotation? Well, the central angle is 120 degrees. And so if I turned it a full central angle, it would look the same. But what if I only rotated it half of it? If I only rotated it halfway, if I did something like a 60 degree rotation, wouldn't that only spin it halfway to that next vertex and turn it upside down too? Is this making sense?
Yeah, thank you.
Picture taking an equilateral triangle, I think in the shapes that came with your activity manual, you can take that triangle and see how far you turn it in order to get, if you hold the middle fixed in order to get it upside down, or how many different ways you can flip it over to get it upside down, okay? If that's all right, I'm going to clear that one and look at number 15. Let me clear that one. Turn my finger back into a mouse and slide the page over. 15 says, A reflection across line M leaves point A fixed. So I've got this line reflection. And when I fold over my line, this will be my line M, there's a point that doesn't move. Well, didn't we say when we talked about line reflections that the points on the line do not move? And so if A stays put, doesn't that mean that A is on the line? So if part B, if A doesn't move and B doesn't move, wouldn't they both have to be on the line? And then part C, over here I have some point C. And when I fold it over the line, which means I'm going perpendicular the same distance away, C ends up at D. Right? If I were to fold, C would land on top of D. Where would D land? If I were to fold my screen along that red line, C lands on D. Where does D land? Where does D end up? Where's its image? Any ideas? Nobody?
D is gonna
Good.
one D reflect on C.
Yeah, wouldn't D fall on C? Doesn't that kind of fit along partially with the idea that we had of symmetry? I'm going to cheat a little bit and go back to that equilateral triangle that we were talking about. And so with that equilateral triangle, we had said that a symmetry line would be the line down the middle. And if I folded, C would end up on D. Wouldn't D also end right back on C? So that the image of one point would be the pre-image of the other. Kind of cool, huh? Better?
Yeah, thank you.
Okay, great. Any other questions on any of this transformational geometry assignment? Some of the problems do get a little bit more involved. But I don't know. By the time we get to this chapter on transformational geometry, and then the next chapter where we start looking at constructions, I almost think they're a little bit more fun than some of the others because we get to draw pictures. We're mostly, so much of what we do in geometry is based on that diagram. And so with this homework, probably more than some of the other assignments and the next homework too, I expect that you make accurate drawings with straight edges. And if you need to make sure that you're reflecting over a right angle, use a protractor. We don't want you to just wing it because you can see when I wing it on the screen how off my pictures are. Do it accurately. Does anybody want to look at anything else from this homework?
Can we go over 34 on page 592, please?
Sure.
All right, thank you.
Oh, I love this question because it takes that idea of symmetry and says, okay, all right, let's think about this. If I talk about an addition table, that would be when you're trying to learn your addition facts. You might put the plus sign here. We might have the numbers 1, 2, 3, 4, 1, 2, 3, 4. We go 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, 1 plus 4 is 5. 2 plus 1 is 3, 2 plus 2 is 4, 2 plus 3 is 5, 2 plus 4 is 6. And we'd keep on doing our addition facts, filling in this table. And as I fill in this table, do you notice that some of the values kind of sort of start repeating? It's almost like there's some sort of symmetry in the table. 2 plus 1 and 1 plus 2, the 3's are in the same place. Same way, 3 plus 2 and 2 plus 3, they kind of match up, don't they? 3 and 1, 1 and 3. Do you notice how if I were to fold this table along this diagonal, wouldn't each number end up on top of itself? And in some ways, a very long time ago, probably before any of you, there was a point in time when in high school, 9th grade math, they included a little bit of, when you talked about your properties, commutative, associative, distributive, they talked about different systems. And one way of telling if an operation was commutative was it had this symmetry along the diagonal, that those values would match up. And so go ahead, draw part of an addition table and show that line of symmetry. Then draw a multiplication table and see what you see. Part C deals with that Pascal's triangle. And I know those of you who had me for Math 108, we did a little bit of looking at that Pascal's triangle. Those of you who had Mr. Milazzo for 108 or took it at a different campus, different school, remember the Pascal's triangle started with a 1 and the end numbers were always 1. And beyond that, any number that was on the interior was the sum of the two diagonally above it. And so then the end would be 1. 1 and 2 would add to 3. 2 and 1 would add to 3. And there's a 1 on the end. And as I keep filling in these numbers in my Pascal's triangle, you notice that there also seems to be some symmetry there. Draw your Pascal's triangle and put in that line of symmetry. Better? Did that answer your question?
Yeah, it did. Thank you.
You're welcome. Any other questions?
Could we please do number 6 on page 602?
Sure.
Thank you.
If the book takes me there. Number 6 asks you to cut a hexagon from a rectangular piece of cardboard stock as shown, using a ruler to ensure that the opposite sides A, B, and D, E have the same length. No restriction is placed on the position of points C or F. Use the paper template to illustrate that a hexagon with congruent and parallel pair of opposite sides can tile the plane. And I'm looking and I'm thinking that that diagram, let's turn the page, shows up on the opposite picture. So do you see over here when I turn the page, you've got this index card. They want you to cut it, use a straight edge to make those lines, And what they want you to make sure of is that whatever length AB is, ED is the same length. You just want to make sure that those two sides have the same length. C and F can go anywhere on those opposite sides. Draw those lines. Cut out your index card. And then see if on a sheet of paper, the way we did with our translations yesterday, we could tile the plane. We could trace over that and completely fill in the sheet of paper with these odd shaped hexagons. So it's actually kind of more of an arts and crafts type of thing. Better?
Kinda, I think I get it, but I don't understand the half turn part.
Half turns means you're going to have to rotate your index card in order to get all of the puzzle pieces to fit together. So you're not going to just slide your index card over. You're going to have to turn it a little bit in order to get those shapes to fit together. So let's see, for example, I don't know if I have the skill to do this or not. I'm going to trace this. And then when I try to translate it, it makes sense that A, B, and D, E would have to match up. And this isn't going to let me slide. I'm sorry. When and I don't think I can slide that thing that I just drew. In order to match them up, I'm not going to just be able to just slide them. I'm going to have to rotate my index card a little bit to get those puzzle pieces to fit together. Have you ever put together a puzzle? And when you put together a puzzle, sometimes you try to fit the piece in and it doesn't fit, and you have to spin it and turn it upside down in order to get it to fit. That's what they're saying. Okay. Any better?
Yeah, thank you.
You're welcome. Any other questions? I think this question number 12 is with the alphabet is kind of fun. Trying to cover a piece, or at least a good section of a piece of dot paper with all C's that kind of fit together. If I look, the idea of half turn would fit in here. If I looked at trying to tile the plane with those letter C's in order to get them to fit together, I might put another C directly below it.
Can you do number 20 on 577?
Sure, can I put it on this picture though? And then I might have to turn that C upside down to get another C to fit in. And so that idea of having to spin them, rotate them to fit. And now what page number was it?
577.
Oh, Lord. And which question number was it, hon?
20.
20? Use dot or graph paper to copy triangle ABC and points O and P. Then draw an image of triangle ABC with the dilation center O that is a scale factor of 2. Well, in order to do a dilation, remember that we need a center. So here we're starting with the center O, and we need a distance. 2 means we want to take each point and move it twice as far from O. So I'm going to take O, connect it to B, make a ring. I'm going to take O, connect it to C, make a ring. I'm going to take O, connect it to A, and make a ring. Now I want to go twice that distance away. And so from O to B, do you see how I'm moving along 2 diagonals? If I double it, wouldn't that take me over here? O to C, it's 2 dots away. If I double it, wouldn't it take me here? O to A, it's down 2 dots. If I double it, wouldn't that take me here? And so now when I connect those points, I wanted to connect them with a straight line. When I connect those points, you see I get this image and it's twice as big. Let me clear that. And then we want to do a dilation with a center of P, scale factor of 1/2. So now I'm going to connect P to each of those points, but instead of going twice as far, I only want to go half the distance. So let's see, from P to B is 1, 2, 3, 4 spaces. Wouldn't halfway take me here? And in the same way, if I were to connect P to A, I'm sorry, my line tool isn't working. I should be doing that with a straight edge. That's 1, 2, 3, 4, 5, 6. So halfway would take me here. And you see how I'm taking half of that distance. And when I do that, it will give me a shrink or a smaller image. Better?
Yes, thank you.
You're welcome. You could probably just do that on plain paper, but with dilations, it's so much easier on graph paper or dot paper, where you can actually like count the number of spaces you move to half or double or triple. Okay. Any other questions from anything in the textbook? If not, how are you folks doing with those chapter 11 activities? Did anybody have questions on any of the activities from chapter 11?
I haven't even been able to start them with the funeral and everything that I had last week going on.
Okay, all right. Again, today I wasn't planning on presenting anything new. It was going to be a working day. If we were on campus, we would have a lot more working days where you folks would just be doing the activities in class, and I'd be walking around in groups, and I'd be walking around from group to group, giving a hand if there's a need. I'll leave it up to you folks for the rest of today. I'd like to make it a working class for you. How we do it, do you want me to put you in breakout groups to work together? Or would you rather just work alone and have me available if you have a question to ask? Do you want to go in breakout groups or not, folks?
I would be fine with just working by myself if that's what anyone else wants to do.
Sure.
Okay, so then how about for the rest of class today then? Let's see. I could put you in breakout groups of one and go in and meet with you individually, or we could just leave working together with this screen, and if you have a question, you can just ask. And you guys, I would prefer probably the latter, because usually if one person has a question, there's somebody else in the room with the same question, and we can be answering the question for the whole class. But if you'd rather talk to me one-on-one, we can put you all in an individual room and you can raise your hands if you have a question. Does it make a difference to you folks?
No.
Okay, so let's just leave this for you then to work individually, okay? And if you have a question on anything, please, 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 please ask. And I'll stay here until, what about you? Okay? And I think if you have a question, you can share your screen also, if you want.
How should we do the first activity if we don't have a mirror?
Do it using the definition. So let me go back to sharing my screen. We had said that if I were to connect, if A goes to B, the image would be the perpendicular. Let's get rid of that line. Would be the perpendicular bisector. So I try to find the midpoint and go perpendicular. So here, for each pair, draw the image of one to the other. Well, these would correspond. These would correspond. If I just connect the midpoints, that should give me that reflection line. These would correspond. These would correspond. If I connect the midpoints, it should give me that reflection line. Okay,
Okay. Thank you.
you're welcome. Thanks for asking.
Can you go over 5 on page 590, question 15?
In the homework?
Yep.
Page 590. Question. Which question number? Which question number on page 590?
15.
What you want to do, give me just a second. I didn't assign 15. If I look over here,
Oh, whoops.
it's 2, 5, 6, 7, 13, 23, 26, and 34.
Oops.
But it's, I mean, let's look at it because it's, I didn't remember doing that on the answer key. If I look at the letters of the alphabet, if I look at a lowercase a, depending on how you draw it, you might have horizontal line symmetry. If I look at a lowercase b, I don't think there's any symmetry there. If I look at a lowercase c, then I have horizontal line symmetry. And as I go on, let's say maybe the letter X, you might have both vertical and horizontal line symmetry, and so on. Better?
Yes.
It's a fun question, but I figured going through the whole alphabet was a little time consuming. So I didn't ask you to do it for that. I think I asked you to do, let me double check. I think I asked you to do 13, which is just instead working with the digits 1 through 9. Yeah, question number 13. I asked you to do it with numbers instead of letters, just because there's fewer, it's a little bit less for you. Okay?
Okay.
Thanks for asking.
How about question 26 on 591?
Okay. Have you ever heard of a palindrome? It's a word that's kind of the same frontwards and backwards. And so if I look at a word written in all capital letters, if a word in all capital letters has a vertical line symmetry, well, that would be like, if I look at the example over here, doesn't that word wow have vertical line symmetry? I could, whoops, if I drew that line in the right place, let's try that again. Couldn't I fold it over a line through the middle of the, a vertical line through the middle of the, wouldn't two have vertical line symmetry? And it would match up. And does it make sense that if a word had vertical line symmetry, it would be the same on either side, and it would have to be a palindrome. The flip side, if I look at that word noon, well, the ends don't have line symmetry, so that wouldn't have vertical line symmetry. It's still a palindrome, but it wouldn't have that symmetry. Dad, like if I fold it along horizontally, if I try to put a horizontal line through dad, the A doesn't fold, the D's do. Instead, if I try to put a vertical line through dad, the A's fold, but the D's wouldn't match up, they'd be backwards. So it's a palindrome, but it doesn't have that line symmetry. Come up with another word where the letters are the same front and back, but because of the shape of the letters, they don't have that line symmetry. So if I look at that word pod, somehow it seems symmetric, but I can't fold it over a line. But if I took that word pod, could I turn it upside down?
Yes.
And if I turn it upside down, does it look the same?
Yes.
So can you remember what type of symmetry we said we had? If we could invert our diagram, if we could turn it upside down, and it would look the same. Remember what type of symmetry that was?
Translation symmetry.
Translation, you applied it. Go back and look in your notes. There's a type of symmetry that we said a figure would have if it looks the same upside down as right side up.
Point symmetry. Point symmetry.
And then find a palindrome with a horizontal line of symmetry. So come up with your own word where the letters match up front and back, but the letters are such that you can fold it horizontally and have it be the same. I think there's a few words that would work. Okay, better?
Thank you.
You're welcome.